Maximum and minimum problems involving boxes. The truth of the matter is that all maximum and minimum problems are solved the same way in that you find the slope of the tangent, set it equal to 0, solve, and answer the question. All we're really doing in the next couple of videos is giving you exposure to different types of problems. So we're going to prove that a rectangle of given perimeter has maximum area when it's a square. We'll organize ourselves by drawing a diagram. We have a rectangle. We'll call the sides X and Y. For those of you who are saying, wait a minute, isn't this supposed to be a square? We're going to prove that it is a square. So if you are proving something, you do not know that it is true yet. So we have to go with the fact that it is a rectangle and the sides must be different. Now, given a perimeter just means that there's some number for the perimeter, and I'm going to call my perimeter P. So the perimeter is fixed. It's not a variable. We're just using a letter to represent the perimeter. Perimeter of a rectangle, 2x, 2y, and the answer for the perimeter is P. We could then simplify that, divide everything by 2. When we do that, we'll get x plus y is equal to P over 2. And our aim is to get y by itself, so we'll bring the x over. We now know what the other side is. So our two sides are x, and the other side is P over 2 minus x. Now, what are we trying to maximize or minimize? Maximum area. So the area of a rectangle, length times width. So the width in this case, P over 2 minus x. And then we're going to take the derivative. Again, you always have the choice of when you want to take the derivative. Would you like to do a product rule? Or is it easier if you expand this first? If we expand it, we get P over 2x minus x squared. The derivative of P over 2x to the 1 would be P over 2x to the 0 minus 2x. And for anyone who's a little upset with what's going on here, P is just a number. So when you take the derivative of a number times x, the derivative is just that number. Another way to think of it, the slope of this would be P over 2, y equals mx. So the derivative is whatever the m was of the slope for the P over 2. All right, what do we do next? Take your derivative, make it equal 0. We'll bring the 2x over. We want to get x by itself, so we can divide both sides by 2. And dividing by 2 is the same as putting another 2 in this denominator. So x is P over 4. If you don't like that, there's another way to think of it. You could think of it as saying, I'm going to multiply this side by a half. If I do that, I'm going to multiply this side by a half. That will give me x is P over 4. Now we need to determine if this is going to be a maximum or a minimum. And this is a little bit strange. How do you work with P over 4? All right, we need something on the left-hand side so that when we plug it into the derivative, we can find out if the derivative is positive or negative. And be careful, you can't go beyond 0. Let's think about why that would be true. We're talking about the length of a line, so you can't be smaller than 0. You can't have a negative length. So what number could we use? We could use 0. Nothing wrong with using 0, so let's put 0 in. And if you put 0 in, you would be left with P over 2. P is the perimeter, so that's positive. So P over 2 must be positive. So on the left-hand side, we're positive. Number on the right-hand side of P over 4. How do you do that when you don't know what P is? Here's how you do it. P is to the right of P over 4. It's 4 times bigger. So let's put that in. If you put in P, half of P minus 2P, negative. So our plus minus chart looks like this. We're rising on the left and decreasing on the right. So it looks like we have a maximum at P over 4, which is what we were looking for. And we have to prove that it's a square. Okay, so when x equals p over 4, what would y equal? We'll put p over 4 in, and then we need a common denominator. So the common denominator would be 4. So that would give us 2p over 4 minus p over 4. So 1p over 4. And again, if you're not seeing that, we'd end up with 2p over 4 minus 1p over 4. Denominator is 4. 2p minus p is p over 4. So what does that do for us? So the dimensions of the rectangle then are p over 4 times p over 4. And that shape must be a square. So when you have a rectangle of given perimeter, the maximum area gives you a square. Let's try another one. 2,700 centimeters squared of material, making a box. The box has a square base. We don't know anything about the other side, so we'll call that y, and an open top, so we're not filling this one. Let's start with this information. The material is, if you were imagining you were putting paper around this, let's say you're gift wrapping it. The question is, how much paper do you need? So we're talking about the surface area. The surface area is the area of the base. So when you find this area, x times x, that would be x squared. And then we have 4 sides left. 1, 2, 3, and 4. And each one is shaped exactly the same way because of our square base. So the dimensions of this, x times y, so the area would be x times y. And we said there are 4 of those. So the surface area, x squared plus 4xy. And the surface area was the 2,700. We need to get y by itself. So what do we do now? Shall we take the x squared over and then divide everything by 4x to get y by itself? So y is equal to 2,700 minus x squared over 4x. What are we trying to maximize or minimize? Largest volume. So volume of a three-dimensional object, length, width, height. Length, width, height. So x, x, and y. And y was equal to 2,700 minus x squared. So we're putting that in place of y. X times x became x squared. Now, enormous warning on these questions. You are in control. You decide when you take the derivative. This would be a product rule involving a quotient rule. I'm not interested. I would multiply the x squared in. So 2,700x squared minus x to the 4th over 4x. And then I'd split them up into individual fractions. That one and that one. Why I would do that is they can simplify slightly differently. 4 will go into 2,700, I think 650 times, and leaving us 625, sorry, x. And this one, we can take an x out of here and an x out of there. That would leave us x cubed over 4. So what did we do again? We took our fractions, separated into 2 pieces so we could split them up, divided this one by 4. Yep, 625. X squared divided by x is x, and then split this one up. So we're going to start with that on the next page. And there's a hint of what's coming. The other thing I might do is I would rewrite this. So when you see x cubed divided by 4, that is the same as saying I have 1/4 times x cubed over 1. They are the exact same thing, x cubed over 4. And why I would write it that way is when it comes time to take the derivative, it's just going to be easier to do. So let's find the derivative. This one, 625. This one, multiply by the exponent, lower the power by 1. And so by not writing it as a fraction, I think we're more likely to see this just as the number up front, and often the derivative is easier. All right, what do we do with the derivative? We make it equal 0, and then we need to solve that. We'll bring this term over. So there's the 3/4 x squared. And then multiply both sides by 4. And we know that number, that's 2700. Divide both sides by 3. We'll get x squared equals 900. What squares to 900? Plus or minus 30. Now, we need ourselves a plus minus chart. So on our plus minus chart, we have plus or minus 30. No vertical asymptotes. Plugging into the derivative. We haven't changed any sign, so we can plug in here. Nice easy number in between would be 0. And that would be a positive because I'm left with 625. Nice easy number out here. How about 1,000,000? That sounds like a good number. Take 1,000,000 squared, multiply by 3/4, 625 minus that, definitely negative. Now I'm not going to bother doing anything over here. The reason I'm not is I'm 100% sure that negative 30 is not going to give me a maximum area or volume, because I can't have a length of negative 30. So do you have to put the negative 30 in? The answer is you have to put it in so that when you're picking a number to the left of 30, you don't accidentally go beyond it, because once you go beyond a critical point, often your plus and minus changes. But other than that, we don't care because we know it's not going to be part of a solution. All right, we have a maximum when x equals 30. And what happens when x equals 30? This was our y value. So we'll put 30 in. That would be 900. This one, 120. When you work all that out, you end up with 15. You can verify that. And have we actually answered the question? Find the largest volume of the box. So these are just the dimensions. So we know what the dimensions are. The dimensions would be 30 by 30 by 15. So 13,500 centimeters cubed. If you'd like a recap of what just happened, we drew ourselves a diagram, figured out the surface area, used that to find the volume. Enormous warning was simplify this a fair bit before you take the derivative. And really another enormous warning, some people get to here and they're feeling so proud of themselves, yay me, look at me for doing all this work, that they forget to take the derivative. So please remember as you go along, look at your notation. If it still doesn't have a prime, you're not done. So keep going, set it equal to 0, do your plus minus chart, and make sure you answer the question. Okay, your job today, it says max-min involving boxes, but truth of the matter is it's a collection of questions, some of which involve boxes. All right, you should have a good day today.